So, hello. This is the introductory lecture for FeatherWeek1. Now, under normal circumstances, the schedule for the semester would have had me do this lecture in front of you in person before you actually ever started to use your kit. Unfortunately, because of the timing of the midterm, you were given the first lab before I was able to do this introductory lecture. And then spring break happened and campus closure and COVID-19, and the schedule's a bit of a mess. So unfortunately, you're already halfway through during the first lab. And hopefully this lecture will clear up some of the higher level questions that you may have had around, like, why are we doing this at all? So I apologize for the out of order, but some of it was not to be avoided. So that having been said, I will also say that I just got done doing a practice version. It wasn't meant to be a practice version of the same lecture, but it ran so long that I'm going to throw it out and I'm going to do it again, and that's what this is. So I will say at the top that if you want to, you can certainly increase the playback speed on this lecture. If it ends up being really long, you can increase it by like 25%. If you find that you can still understand everything just fine. So it's up to you. You have control of being able to pause and speed up and slow down. So that's actually one good thing about doing a lecture this way. So let's get at it. So the big question is, you may have heard of the term embedded systems or embedded programming before this. That's basically what this portion of the course is. You may kind of be wondering, so how is this different from what I've been doing? And in some respect, it's not different at all. And in some respect, it's fairly different. So they're two different flavors of the same thing. But you've been preparing for this by what you've done so far. It's just different. So the first distinction to be made is, so how are the PC type programming that you've been doing so far, how is it different from this embedded programming? So what does embedded mean? So start with PC. So a PC, as you should all be fairly aware by now, is the PC was not designed really to just do one specific thing, and that's majorly how it differs from what an embedded system is designed for. An embedded system is designed to pretty much do one thing, and to do it well, and to do it small, and to do it cheap, and to do it fast. Whereas a PC, there's hundreds of things you can do with it. So with that flexibility comes a lot of pluses and minuses, and we'll talk about those more in detail. But I want to talk more about, I mean, you're already fairly familiar with what you're using your PC for. Obviously, you're using it for email and social media and writing lab reports and using CAD tools. As an ME30 person, you may not really be using too many CAD tools and stuff yet. But so you certainly have a sense that you're going to be running, mechanical oriented design tools in future semesters on your laptop. And your laptop is the perfect place to run that. Whereas embedded systems are used mostly for control applications. So very specific, narrow set of tasks. So let's take a look at, I have a couple of, so this is your standard PC type system. This is, you're all used to this. It's this big, it costs this much, you know what it does. So as opposed to embedded systems. So these are kind of some classic embedded systems. I found this graphic on the internet just an hour or so ago. I don't know how old it is. Okay, it's 2 years old. I would say this graphic could be 10 years old because there's so many more things that embedded systems are now than these, but these are kind of the classic ones as of like a decade ago. So as you can see, these have very narrow use cases. A digital camera is one thing. It takes pictures. So nowadays, digital camera, not only does it take pictures, but it also pushes the data up to the cloud via some sort of wireless protocol like Wi-Fi or Bluetooth, more than likely Wi-Fi. GPS receivers, DVD players. We don't even use DVD players anymore. MP3 players, don't use those anymore. Microwave ovens, we still use those. Photocopiers, you're probably not using a photocopier that much. Gaming console, no. Set-top box, almost not. Wireless routers, yeah. Okay, so industrial robots, hopefully, if you're a mechanical engineer, that's a good area to be in. That's where there's some decent pay in that. So embedded systems move very quickly. I would argue that the PC hasn't changed very much in 20 years. Clearly, it's gotten faster. And yeah, there's some more things you can do with it faster, but what you can do in an embedded system now has grown by leaps and bounds, or it's actually shrunk by whatever the opposite of leaps and bounds is, micro steps, nano steps. So it's funny because you might think about your cell phone as being an embedded system. And we'll talk a little bit more about that later. But I would argue that 7 out of the 10 things on this, probably 6 out of 10 of the things, can't use your cell phone as a microwave oven yet. But almost everything else on this, you can use directly or indirectly from your cell phone. So some embedded systems, so this is just the evolution of technology. Some embedded systems just evolve away, right? We don't use typewriters anymore. We use PCs for that. So most of these systems, while they were great when they came out, they've evolved. And now we have one device that it probably costs as much as the sum of all these things together nowadays. But I would argue that smartphone, well, we're going to talk about it down here, so I'm not going to steal my own thunder here. So let's talk about kind of what the range of embedded systems are now that we're seeing both at the higher end and the lower end. So as far as tiny appliances are concerned, the low end of this is, there are Bluetooth toothbrushes. There are, I haven't used it. I got one at a trade show from a vendor who made the microcontroller that was inside of it. There's a razor that I guess is battery operated. And I guess it's got a motor in it. It's like a regular blade shaver, but for some reason it's got a microcontroller in it. So there are microcontrollers in, things that you stick in your face and on your face. But the tiniest microcontroller appliance that I can think of is something that you've actually been using for decades, and that's RFID. So an RFID, an RFID tag is either something that is put on products in the store so that if you try and walk out with them, the alarm goes off. But RFID tags, more the ones you think of are those little key fobs that hang on your keychain that you hold next to a little pad on the wall that allows you into the building during a specific set of hours, depending on who you are. So the way those things actually work is electromagnetic energy, radio waves, are basically sent out as energy to the key fob. The key fob captures that energy. It boots a little tiny microcontroller that's inside the key fob. It runs a little program and it sends data back out using that energy that it harvested during that split second back to the pad that's got a reader in it, then transmits that data across a wire or network back up to a computer that then asks whether you should be let into the building or not. So there's believe it or not, there is a tiny microcontroller in there. And some of these RFID tags are not even, like I said, they're powered from the radio waves. Some are larger and have batteries, like maybe the one that gets you into your parking garage. You've got a card-sized one. It probably has a battery in it. But this is pretty much the minimum cost and complexity of an embedded microcontroller product now. And RFID tags at their cheapest, especially when they're used for inventory control, are on the order of like 5 to 10 cents. So that shows you kind of what the new low-end range, that range is not represented in this graphic, but that is the current low-end range of where microcontrollers fit in the grand scheme of computing and consumer devices nowadays. So the high end is higher than it used to be. So I would argue higher than anything that's in this graphic. What's the most expensive thing in this graphic? Photocopier, maybe. No, industrial robot. Industrial robots, okay, that's pretty high end. So let's think even bigger. So nowadays, harvesting combines, cars, trucks, autonomously driven or not, earth-moving vehicles, autonomous or not, and some of these are definitely autonomous, are examples of embedded systems. So they've got microcontrollers in there that control, if not the functions under some sort of external control, but maybe autonomously make decisions about what's going on in their environment and what their goals are and what they need to do. So the range of embedded devices is massive. I mean, in terms of order of magnitude of cost, there's probably 9 orders of magnitude there. I can imagine an earth-moving vehicle being tens of millions of dollars. Millions of dollars. And like I just said, RFID tags are 5 to 10 cents. So however many orders of magnitude that is. So we also see embedded devices now that we didn't see 10 years ago, particularly around home and building automation, security, things like that. So entry control, I already talked about the RFID fobs. There are little remote devices for home security that detect glass break. They have microphones in them. They listen to the sound for glass breaking, and then they report that, just like a much simpler device that just detects when a window's been opened. That just uses some sort of magnet to detect when the window slid up and move the magnet out of the way. So this is another example of a device that's now enabled by the type of devices that you're going to be working with now in the next couple of weeks that we weren't able to do before for cost or size reasons. Some embedded systems are designed to look for suspicious movement or behavior. Most of these have image sensors. Some have very crude sensors, or sometimes they just detect when somebody moves in or out of a room. But at the high end, there are systems built into video cameras in airports that look for people walking around suitcases that clearly aren't theirs. Another example of something that is affordable and that you may have run into is a Nest thermostat. It's got a microcontroller in it that not only does it have some sensors in it that look and see what the current temperature is, but it also kind of learns from your patterns when you tend to come home and turn it on, when you leave, because it's got some motion sensors and stuff in it. So all of this information is gathered up, it's grinded up by a program that somebody wrote out there, and is used to perform some very specific function that saves you money, time, aggravation, provides an extra level of safety, whatever. So pet and child tracking is another example. It is very feasible now through cellular communications devices built into something the size of a key fob practically, that you can hang on a kid. It's either stick it in his backpack, tie it to a shoelace, wedge it in his underwear, wherever, that if a child gets a certain distance away from you, because you have a similar device that's cooperating with this thing to detect when your child gets too far away, right? You typically don't want your pet running away or your child disappearing into a Chevy cargo van with some weirdo inside. So these are a lot of the types of systems now that are enabled by all the cost advances that have been made in computing over the last number of years. So the way in which the programming of embedded systems is different versus kind of what you've been doing is embedded systems tend to deal with things happening in some kind of random order, and sometimes the timing in which these things happen is important. So whereas if you're writing a program in Python right now to read the contents of a file and do some sort of data transformations on it, come up with some new data and then write that out to a file or maybe out to the network or something, it's pretty much of a straight line program. You pretty much know the order of what's going to happen. You're going to open a file, you're going to read it line by line probably, you're going to do some processing on each line, and when you stop getting lines because you got some sort of end of file exception or indication, you close the file and you're done and your program exits. So embedded systems generally don't work that way. Embedded systems often, and in some cases, they have like no user interface to them at all. Or if they do have a user interface, there's no notion of when does a program start and when does it end. A lot of embedded systems, like say take your microwave or your ceramic stovetop or something, as soon as you put power on them, they start running their program. And they don't end until power goes off. And when power comes back, they start running again. So these are programs that execute forever. They basically never exit. There's no falling off the bottom of the program and getting another command prompt where you get to run another program. So typically the outside, and I think you've probably already seen this in the first lab if you started it, is the outside of a program is typically a while true loop in Python. And then all the logic is somewhere inside of that loop. And once it goes through that logic, it just goes back up to the top again, and it decides what it needs to do next. And a lot of times through that loop probably represent nothing happening. So the body of that loop might be, has this button been pressed? Has that button been pressed? Has the door to the microwave been opened? Has the timer gone off and I need to start to beep? Has the humidity sensor inside the microwave reached a level that I think the food is cooked and I should just shut off because I'm in some sort of automatic cook mode rather than a timed one? So a lot of the passes through that loop are going to be no button was pressed, basically nothing changed since the last time. So a lot of passes basically manifest themselves in nothing happening. And then when something does happen, one of those if statements that represents the testing of a button being pressed or some sensor reaching some value, like the humidity went up, I know my food must be cooked because the water started to vaporize, then those if statements then start to kick in, and then some other events happen that cause buzzers to beep, or the radiation shooter, what the heck's that thing called? I forget what it's called, to turn off because the food needs to be stopped cooking before it dries out or starts on fire. So that's basically how execution of a Python program in an embedded system differs. So I've already talked about, the outer while loop, and a lot of stuff you'll see inside that while loop is typically a bunch of if statements that are testing conditions that may have happened such that something needs to happen in response to that. So something happening is generically kind of called an event. So this style of programming is, rather than straight line programming, like reading a file until all the data is gone and then closing it and being done, this style of programming is called event-driven programming. So things happen when events happen, and nothing happens until event happens. And so the life of an embedded systems program is basically figuring out what has happened and then using that information, given the current state that the machine is in, that the program is in, to determine what needs to happen next. So you can imagine that there's an input, there's a electrically connected switch in the door that the microwave can detect whether you've opened the door or not. So typically there's going to be 3 modes that the system's going to be in. It's going to be in a state where it's not doing anything and it's waiting for you to open up the door. That's often the first thing that you do. So it waits for you to open up the door, and then clearly the next thing it makes sense for it to do, because it shouldn't do anything in the meantime, is to wait for the door then to be closed. And then it goes into this mode where it's basically, okay, I know there's something in the microwave, or I'm guessing there's something in the microwave. Now I can accept keyboard input. So it didn't make sense to accept keyboard input when you were in the initial running state where there was nothing in the microwave. It hadn't even, nothing, the door hadn't been opened the first time. So the act of getting a key press is the same, or detecting when a key is pressed, but when you're in that initial state of nothing being in the microwave, you pretty much want to ignore those keystrokes because you really can't kick off the use of the microwave until something's been put in the microwave. So that doesn't go for setting the clock and stuff. So we've got a simple microwave. So point being that there's a lot of interplay between detecting the events and knowing what events need to get acted on and how they need to get acted upon, given the current state of the system. So, like I said, this is called event-driven program because the flow through the program is driven solely by the events that happen, which are not predictable in all cases, rather than the types of predictable programs you've been writing, like, okay, the worst thing that can happen in a program you're writing to open a file and read it and process some data is, okay, the file isn't there. Okay, then the file open fails, and you're done with the program. You just say, hey, I can't run the program because that file you asked me for wasn't there. That's pretty simple. The next thing is, okay, you read through all the lines. What could happen? Well, I guess if it was on a flash stick and you tried to read a line, then the read might fail because you took the flash stick out. You took the data away. So in some respect, that's kind of event, but for the most part, the control flow through the program is top to bottom. Whereas in an embedded program, an embedded systems program, you have this loop and you just check for stuff that happened and then decide what needs to happen next. So that's how the style of programs differ. And that part is significantly different. What isn't different is it's all Python. The syntax is all the same. You know how to do ifs. You know how to call functions. And if the system was designed nicely, it's really easy to get access to the events that happen. Like you can ask in a function, you can ask the question, was this button just pressed? And as long as that happens, it's all just software at that point. You just practically don't even care that there's hardware there because you're just calling software functions in a Python. So one of the other ways in which embedded systems programs can be very different is that some embedded systems are literally embedded. They are stuck in your body, like a pacemaker. So a pacemaker, not only does that program have to work functionally, I mean, not only does it have to be correct, but it has to operate given some fairly short time frames. So I suspect, I don't know that much about pacemakers, but I suspect it's always listening to your heart. It's probably the events that it's looking for are probably not as simple as, did the heart beat? Right? I'm assuming it's looking for other things like sub heartbeats, or maybe it also sets a timer that if it doesn't hear a heartbeat within 3/4 of a second, then that in and of itself is a heartbeat, right? It's a timer saying, hey, listen, I didn't hear a heartbeat well within the amount of time that I should have gotten another heartbeat. I need to kick in and do something. So in some respects, some events can actually be self-generated. So setting yourself a timer for some point in the future is of itself an event. It's not an external event, but it's an internally generated event. That without it, you can't really implement a program to perform the function that it's being asked. So some of these types of systems have operating systems inside of them, which are called real-time operating systems. And you probably know, obviously, that Mac OS operating system, Windows, it's an operating system too, provide a whole bunch of services. So Python itself as a language provides a whole bunch of services. It's just that most of them tend to be around data and declaring functions and stuff, right? So you ask for a list, you get a list. You ask for something to be appended to a list, it appends something to a list. So in some respect, that's an operating system. It is doing some stuff on your behalf that are so menial, so low level, that you really can't be bothered. At some point in time, you gotta build a building with bricks. You don't build a system with atoms. So the operating system is a bunch of, or the Python runtime is a bunch of stuff that your programs sit on top of, a bunch of services that you make use of. So a real-time operating system is a different type of operating system. It's similar enough to Windows. I mean, it's all just function calls when it comes right down to it. But a real-time operating system has features in it that ensure that things get done in the order in which they're supposed to. So it's a little bit of a different way of architecting a system, but you can imagine that if you're a pacemaker, job one for the pacemaker is to keep that heart going, right? And if you don't keep that heart going for whatever reason, you failed, right? Whether the program had a bug in it, not really what I'm talking about, but you need to make sure that if the heart beats or if the heart doesn't beat in a certain period of time, you need to kick in and whatever else you might have been doing at the time gets done in the time frame that it needs to get done, that you programmed the system to get done in. So an example of this is, let's say that, and this happens, pacemakers have their software and they get updated. So the last thing you want is to be updating a pacemaker and have it be downloading a program and have it do nothing in the meantime until the update's done, right? That would clearly be fatal. So what real-time operating systems afford you the luxury of is being able to say that this part of my code is the most important part. This needs to keep running regardless of whatever else is happening. So in a real-time operating system, you actually write a bunch of different functions that do specific things, and the real-time operating system then calls those functions according to the priorities that you've dictated in your program. So in some respect, the organization of how to write an RTOS program isn't the same as Python, but also there are some ways in which it is. And unfortunately, you're probably never going to get to this. You may not even get to this in 106, but it's how a lot of other things, in fact, inside your PC work. So there are event-driven systems that are fatal or can be fatal, and there are event-driven systems like using your mouse to interact with your PC. That's an event-driven system too. Your PC isn't doing anything until the mouse is clicked pretty much, or it's moved around. Pacemakers are pretty much the same way. There are things that are important that need to get done, and the RTOS ensures that those things happen with the highest priority, and they ignore everything else that happens in the meantime. So the Python runtime, the Python language itself, I'm going to kind of hand wave over the difference between those two, are in some respect is like an operating system for you. So clearly, one thing you can't have happen is to ever see a situation like, application not responding, right? You can afford to suffer that fate when you're browsing. If you don't get to see the web page in 20 seconds, it's not that big of a deal because your PC is off doing something it decided is more important. But this is a reason why in RTOS, why Windows is not an RTOS, is because it just doesn't have the level of granularity of control to be able to know which things are more important than others. It takes a stab at them, but it doesn't do a particularly good job, whereas real-time operating systems do. So I've already talked to some extent about, kind of what's an embedded system and what isn't. So the kind of the classic question, I would normally do this interactively. I would typically stand in front of the room and ask, so what else are some examples of embedded systems and what are bad examples of embedded systems? So one of the typical ones that comes up is a smartphone. Is a smartphone an example of an embedded system? And in some respect, I would argue not. I would say a phone, pre-smartphone, I could argue would be an embedded system because its task was pretty much to make phone calls. Yeah, you could also make text, send text with it and receive text with it. But for the most part, it was a phone, and that's pretty much the only thing that it did. Smartphone nowadays, it does everything. You can load apps onto it. You can run a bazillion different apps. To me, it's just a PC that's just shrunk down. So I would argue at this point that a smartphone is not an embedded system. However, because of all the processing power that's in a phone and how much it's doing, even while you think it's idle, like it's listening to the radio to see if a cellular call is coming in. It's checking the network to see if there's a Facebook announcement or something that got made that's in your feed, right? It's actually doing a lot of stuff. The problem is all that stuff takes energy. So within a phone, there are embedded systems. So for instance, an embedded system might be, so there's basically a micro embedded system that checks to see whether you've pressed the on-off button or not. So there's probably a microcontroller. It's doing other things than just checking the buttons. Well, there's probably one microcontroller in there that's checking all your buttons and maybe checking some other things like the light level or something that's coming through the light sensor on the phone, in addition to the camera that's there. It's probably not dealing with the camera, but the point being is that there are microcontrollers running their own sub-programs inside of the phone that, because they are so much smaller and run at so much lower power, the system, when it's in your pocket and it's doing a lot less. If it was running all those button checking functions using the main processor, then it would be using a lot of your battery. So what the system does is it delegates a lot of these other smaller housekeeping tasks to smaller microcontrollers, very similar to the one that you're going to be programming, that does all the things like lighting the little status LED that says whether you've got there's a cell tower in range, or checking to see which button on the side of the phone you've pressed or whatever. So I would argue that a smartphone itself is not an embedded system, but it has its own embedded systems within it, which is kind of a crazy thought when you think about it. The other thing too is what I consider a Tesla to be an embedded system. Maybe something before a Tesla I would consider to be a little bit more of an embedded system, but nowadays I'm not sure I would necessarily consider a Tesla an embedded system. You can watch a movie in a Tesla, and you can take your hands off the wheel, and if you do both at the same time, you may not survive, but I would argue that a Tesla is becoming more and more like a general purpose computing device than a car anymore. You can argue whether that's good or bad. So anyhow, so how is a microcontroller or a microprocessor based system different from each other? So a microcontroller is basically what's on the little black board that's part of your kit. Microprocessor is typically something more like the processor that's inside your PC. So a microprocessor is some fairly gargantuan sized device that has a buttload of processing power in it. I mean, it can detect faces coming through the data stream from your webcam. It can run simulations, and it's not a cheap device. Cheapest CPUs, 40, 50 bucks, and the high-end ones that go in servers are $2,000 to $3,000. And you just pull your car up to some friendly Intel dealer, and you can have yourself a microprocessor for that price range. Microcontrollers, on the other hand, are they're quite a bit cheaper. Let's page on over to one of these tabs. This is an example. This is the smallest one that I can think of, and this one's even been out. I remember when this one came out 5 or 6 years ago. This is a tiny sub 2mm by 2mm processor. So not only does this thing have computing resources in it, but it also has some memory, and it has both working memory, it has RAM in it, and it also has flash in it for storing programs. Now I probably shouldn't even say programs because it's small enough that basically it only has one program in it. So it has a program in it, and it is, I happen to know that if you buy 100,000 of these at a time, you can get them for 40 cents a piece. However, if you buy one at retail, you can get it for $1.36. So clearly this is 1,330. So this is 2 to 3 orders of magnitude cheaper than an Intel processor. Can it do as much as an Intel processor that's in your laptop? Heck no. But then again, you can't stick this thing in a thermometer, which you stick into your mouth. And you can't do that with your PC. So every computing chore requires a different amount of horsepower. And for things like digital thermometers that can run a little 4-digit display to display the temperature and to read the sensor that is the temperature sensor and shuttle that information to the display, this is all you need. This is for $1 for this part of the hardware, that's what you can do with a microcontroller. So clearly it's in a different market space from what a microprocessor is used for. Is there anything else interesting to see here? Nope. Okay, let's go on. So I've already talked around this a little bit, but you've probably already gotten the sense that embedded systems and the programs are pretty much always about control and interaction rather than data processing. Now, this isn't to say that they don't do any data processing. They might read a sensor 10 times a second and average the values, like a temperature sensor, to check your temperature. So it deals with a bunch of floats, may put them in a list. It may call the average function or whatever the function is called. I don't remember what it is, and they get the average of a list. But data processing tends not, for the low end, tends not to be a major need of a microcontroller. Now, the range of microcontrollers does go pretty high, so that isn't always the case. Once you start dealing with high quality audio and certainly video, you're dealing with a large amount of data. Even though the task it's performing is pretty narrow, right? It might do face recognition or presence detection to see if anyone's come into the room. There's certainly a fair amount of data involved, but from a functional point of view, it's more about control than it really is about data processing. So typically an embedded system typically has a couple of inputs and it has a couple of outputs. And you're pretty much concerned, as I mentioned before, about the order in which these events happen and how to handle them. And the inputs, for the most part, are sensors. Most embedded systems are meant to interact with the environment, and that involves some sort of sensing. So whether that's through the pushing of a button or a switch, temperature sensor, light sensor, speed sensor, like if it was on an axle on a car, it might be detecting angular velocity, some sort of audio or speech input, like an Alexa device. It's listening for a keyword, or maybe an image sensor. Feather, for instance, is actually powerful enough, the one that's in your kit, to do some low resolution image processing. It has enough memory and processing power, which we'll talk about later, to be able to do some rudimentary things. It's not going to be doing face recognition itself, but there are some things that it can do. Some other types of inputs are communication. So getting input from Wi-Fi or Bluetooth or some sort of wireless protocol is another example of an input. It's not a physical input, but it's an input nevertheless. Outputs may be, actually there's typically a lot of analogs between input and output. So audio out is the opposite of audio in. So obviously audio and sound and music and stuff is a standard output. Heat, generating heat either through some sort of, say your stovetop obviously generates heat. Anything that's electromechanical, so any sort of motorized instrument, anything that's hydraulic or pneumatic, almost necessarily is done mechanically through a motor. That's not always true. Some can actually be done, I guess if you go down to a level low enough, they're pretty much all mechanical now that I think about it. Some might be if you use induction, then there's no mechanical action going on there. So even the generation of heat can be done through induction. And similarly, communications, the same communications you use for input can be used for output. The basic control of a program is, typically, as I've mentioned before, it's typically if this happens, then go and do that. Or if this happens, then that happens, but only when there's other things going on, then should this fifth thing happen. So not only does it take the events, but it also uses the current state of the system to decide what the output should be. So, and the actions that are going to happen depend on the current state of the system. Now, I think when I went through this before, okay, so this is what's called a state diagram. This is a way of graphically modeling a system, either to get it straight in your head, or there are actually tools that you can draw diagrams like this, and annotated properly can actually generate Python code. So this can be a mechanism for doing graphical input programming that generates code that's Python or C or whatever, and can generate a program that can run in an embedded system. But basically what this is this is a graphical representation of, so this one here is a very simple system. So it looks like it's got some sort of push event, it's got a coin event, it's got another push event, shows us what state the system starts in, and it's got some coin. So apparently it's taking coins in. So this looks like a vending machine. So you apparently start in the state where whatever's in the vending machine is locked into place. And you insert a coin, and it can then unlock whatever you've basically paid enough for. Or apparently This probably isn't the greatest interpretation of this particular state machine. I don't have any explanation of what this thing is. You can also put in multiple coins and it goes into some other different unlocked state. Okay, so unlocked, I guess, in this context means it's basically uh, thinking about dispensing something until you put in sufficient coinage or whatever. And then eventually you apparently push a button, and then a side effect, an output of this button pushing would be to eject whatever it was that you had properly paid for. And the button that was pushed determines which screw to turn to push the bag of Cheetos out so that it falls down into the bin at the bottom. And then it goes back into a locked state. So this is a really simple thing. Another example, classic example of a simple state machine is if you've got one of those little modal tactical flashlights, right? It starts off, you press the button once and it turns on low bright. You press the button again, it goes to high bright. You press the button again, it goes into a flashing mode. You press it again and it goes off. In fact, this is a classic example of an exercise that you'll do in ME106, but you'll probably even write this in ME106, depending on who you have. I know we teach this pretty much every semester. So the event is the same. It's one button. This is an embedded system that has two things. It has a button, one button for input, and it has one LED for output. Clearly, it's got a microcontroller in there because there's some intelligence about how that output is produced. So one click moves you from a state where the thing was off, so it basically puts it into a state where it flashes the LED at a low enough level that it's basically only providing a little bit of light. So that's kind of your dim light level. You press the button again, and knowing that you were in the dim light state, it knows that you should go to the high light, the bright state. So even though it's the same input, you have to use the cross product, the combination of the current state of the system and whatever inputs are provided. Now you could also envision that you maybe have a flashlight that's got 3 or 4 buttons on it, or a dial on it that it has multiple control mechanisms. So it's got more than one input or output. But a flashlight, a modal flashlight, is a great example of a one input, one output system, where a state machine can help you figure out how to write the code correctly rather than trying to figure out all the combinations of ifs, thens, and elses from first principles. So there is a very mechanical procedure, and I mean mechanical in a less than fully engaged intellectually scope, that you basically can look at a state machine and it makes it a lot easier to figure out how the syntax of the program itself should be written. And you'll do this in 106. So that's kind of key to an embedded system. And then there's a last thing, I'm not going to talk about this in too much level, but so there's kind of a new type of system that's called a machine learning system. And rather than structure your program in such a way that it's just a bunch of if then else's, you basically take a vector, a list of inputs, and you can push them all into a matrix. And the matrix then burps out a bunch of outputs. And so you can kind of think of this as kind of an extrusion kind of thing. It's a meat grinder. So you stick in a whole bunch of data, and the grinder itself has the intelligence to figure out what the output should look like. So I realize this is a little abstract, but basically the logic part of a conventional program just becomes a mathematical, like a 3 or 4 dimensional mathematical problem that just given a whole bunch of inputs in one state, you get a bunch of outputs that tell you what the system should be doing. And the process of making this grinder is a very computationally expensive process. There's basically a training phase that you plow a whole bunch of data into a very smart program that figures out all the correlations between the inputs. And along with the inputs, you also have to tell it, so given this series of inputs, what should the output be? And you basically train this model to understand what should be done given a particular set of inputs and in all combinations. And by plowing like millions or billions of combinations of all these inputs and annotating them such that it knows, you teach it what the output should be, you basically made a grinder so that you can then take this big array of data, it's like basically it's like a two-dimensional list. It's a that you you push your inputs into the list. You basically ask um, so there's an in operator, right, in Python, where you can ask if an item is in a list. So this is like an in operator on mega turbo giga steroids, where you basically say, here's a whole bunch of inputs into a blob of data, and it gives you a bunch of outputs out, which are what the system should do next. And the process of making that model is called the learning phase. And then what you typically embed in a system, like maybe like a Feather, you embed that model so that the only thing that the embedded controller has to do is take the data, run a mathematical operation on it, which is a little bit data intensive, and it tells you what to do next. So the process of going through the arduous sequence of tasks of if this, else, blah, 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 what state am I in, is basically becomes a data processing model. Now, this is a fairly new thing, but it's getting to the point where a lot of systems nowadays do learn behaviors. I don't know if I mentioned it already, but the Nest thermostat does some level of this. It learns from you using the thing for a couple of weeks or months. When you come home, how long after that you tend to turn on the air conditioner or the furnace, given what temperature it is, and it basically learns from your behaviors. So given the cross product of when you come home, what the current temperature is, maybe what time of year it is, maybe what time of day it is, it then just burps out an answer that basically says 14 minutes in the future, I should turn the air conditioner on and the level should be set to 66, right? So the process of learning, so I believe, I'm not a positive, I don't know if the Nest thermostat does all this learning on its own or if it sends the data up to the cloud to basically help make the model. But the end result is there's not a lot of if then elsing that goes on. It's basically, it takes the current time, the current status of whether you're present or not, when you came in, and it feeds that whole vector, that whole list of information in to this blob, which then turns it into a list of things that need to happen. So the outputs might be what the temperature should be and how long I should wait to turn it on, and maybe which rooms that I should turn on, because when Joe came home, he always just turned on, he always wanted the air conditioner based on his presence to be in the living room, right? So working in conjunction with presence sensors in other rooms, and I also believe there's Nest products that do this. They tie into the thermostat that can also use other inputs like which rooms you're in to optimize the air conditioning, such the air conditioning may only have to work in one room, saving you energy and money. So that's an example of a machine learning system. You're not going to be doing that. That's a very computer sciencey thing. However, I do happen to know, I just heard from one of the other professors that there's a professor in the mechanical engineering department that is designing right now a machine learning course in the mechanical engineering department. I don't know if this is a graduate course, if this is going to be maybe a junior or senior level course, but machine learning is coming to a course near you if that's the track you end up going down. So keep your eye out for that. I've already mentioned a little bit about a cloud service. The reason why cloud services kind of need to be mentioned a little bit is that there are some levels of processing or information grinding that just can't be done in a microcontroller. And so a lot of microcontrollers basically act as kind of client slave devices that they're there. Their main goal is to gather up a bunch of data through its sensors, maybe make some local decisions, but perhaps the bulk of the data is sent to a cloud service for some high-powered processing. And speech recognition right now is kind of one of these classic services. I believe also some of these video cameras can also be used to detect human presence, and some very simple presence sensing can get done locally, but some more sophisticated things require processing that can really only be done on servers in the cloud. So point being here is that sometimes an embedded system is just a vehicle for shuttling data to a service that's running somewhere else that then sends information about what the microcontroller's output should be. And one of those things you can imagine, if you never come home at 11:15 in the morning, then your Nest thermostat knows that, hey, listen, this is a very unusual event, and I should maybe beep a little noise on the Nest so that you know that you have to come over and maybe type in a key code or something to get it to not blow off a full-blown alarm for your apartment, and or to call the police automatically for you. So, right, if you don't know what the magic key code is to type into your Nest thermostat, then the local system does a little beep, and that's some local processing, but then it perhaps sends off an image to the cloud that it perhaps forwards the police so that it knows who to shoot when they get there. And hopefully they recognize that it's not you when you also ran home because you got a notification on your phone that somebody was in your place that wasn't expected. So that's an example of some processing sharing that may go on between the local device and the cloud device. And there's a little bit here, a little bit of text about, that I'm not going to go into now, about other ways that why this is a good thing and other ways to handle this. But one of the things that you should definitely pull out of this part of the discussion so far is that, PCs are good for a lot of problems, but they're not the perfect solution for everything, for cost reasons, size reasons, power reasons, etc. And there's just a lot of applications that can be enabled by really small devices that you can basically build for a couple of bucks. So we're going to talk a little bit about the kit now. The kit is it's composed of 3 boards, as you already know, since you've started the lecture. If I was doing the lab, if I was doing this lecture in real time in front of the class, this is the point at which I'd pull out the kit because you wouldn't have done the lab already, or at least started it. But I'd be showing you the kit and all the things that it can do. So clearly, you know from the lab already that there's one board on there that's the black board that contains the microcontroller, and the other boards are made by me, designed specifically for this class and for ME106. So the microcontroller itself is capable of running a shrunk down version of Python called CircuitPython. So the short history of this is that CircuitPython is actually a variation of a previous version of Python that's still in use today, and it kind of competes with CircuitPython, called MicroPython. And MicroPython came about because, it's funny, it came about over like a $5 bet between 2 guys. One guy basically said, there's no way that Python can ever be put on a microcontroller that's got, that you can get for $2 or $3. And he's like, oh yeah, $5 says I can. And a year later, and a bunch of money that he got from a Kickstarter, he funded the development of a version of Python that he wrote from scratch that is small enough to run on microcontrollers that have much more limited processing power and memory than a PC does. And that's the short history of how Python now runs on processors that cost $3 versus $300 from Intel. So the company that we get the blackboard from, the black feather board, the black microcontroller board from, is Adafruit. They happen to be located in New York City. They're a pretty cool company. They're pretty hip. They might be a little too hip, but they're a very, very interesting company, and they're doing a lot of very cool stuff. So the board itself is called the Feather M4 Express. Feather because it is a feather format board. We'll be talking about that shortly. M4 because that is the class of ARM microcontroller, as opposed to an Intel microcontroller that the guts of the microcontroller is built around. And Express in this context happens to mean that it has an extra flash chip on it that enables it to store programs that to store Python programs and run them. So there are other boards that they sell, whether they're Feathers or not, that don't have Express in their name, which I just found this out actually by looking through the website to make sure that Express meant that it always runs MicroPython or CircuitPython. And if it doesn't have Express in it, then it can't, and that's not true. So there are boards that don't have Express in the name that are capable of running CircuitPython. So if you were to buy another Feather, because it has other features, which we may talk about later, like Bluetooth in them or Wi-Fi in them natively, then just because it says Express, just because it doesn't say Express doesn't mean it can run CircuitPython. So you have to look at the product description a little more closely. So most Feather boards, so Feather is that size of board, that shape of board. Most Feathers can be programmed in CircuitPython. CP is short for CircuitPython. So we're using Python for a lot of reasons, but the primary one is it's a very popular language right now, and it's significantly easier to use than what we used before, which 10 years ago was significantly easier to use than what back then only double E's and compies were using to do embedded systems. So the Arduino blazed a lot of great territory, a decade, probably maybe even close to 15 years, 10, 12 years ago now, maybe 15, that they blazed a lot of new territory in terms of making it easier to use for non-programmers, non-engineers, as well as getting the price down. So we owe a lot to the Arduino folks, but they're still pretty much wedded to C and C++ for most of their systems, their boards that they produce. And Adafruit has done a lot to advance the use of Python on embedded systems. They weren't the first. The guy who came up with the software that is MicroPython also did a board. So technically he was the first one to put all this stuff together. But Adafruit's done an extremely good job of making it even easier to use and getting the cost down and basically just getting a lot of feedback from users that the MicroPython project never had the bandwidth to be able to do. So in that respect, Adafruit's done a bang-up job. So the prices for these things are very reasonable. That black board we'll see on the website here itself is $23 unsoldered, unshipped. And it contains the microcontroller that you can buy at retail. If you want to buy one of those microcontrollers, it's somewhere between, it's basically mid $4. And they put all the supporting circuitry and stuff on it, and you can get it for $22.95. So it wasn't that long ago. It was just a decade ago before the Arduino came out that you couldn't get anything like this for less than 100, 150, maybe even 200 bucks. And the prices, of course, on all this stuff have just come down precipitously, just like everything else in computing. That the cost and the power and everything is just it's shrunk to virtually. This is, relatively speaking, this is nothing compared to what it was. So we use the Arduino for this course and for ME106 for pretty much near a decade. I don't want to say coincidentally or non-coincidentally, but I was part of the 2 or 3 people that transitioned the courses from what they were using before to the Arduino, and now here I am 10 years later doing it again, moving that off of the Arduino onto Feather shaped and sized boards that now run Python. So I got to tell you, it's a lot easier to use than even the Arduino, and the Arduino was a lot easier to use than what came before it. So this is where decades, billions, and maybe even trillions of dollars worth of R&D has resulted in a lot of ease of use for you and I to do cool stuff for a couple of bucks. So I did have a paragraph here that I talked about during my practice about the different ways that you can connect accessory boards to Feathers. I'm not going to talk about it. but I will talk about feather wings. Feather wings are the cute name that Adafruit gave to accessory boards that plug into feathers. So you probably know from your first lab already that there's not a lot that you can do with just the black board by itself. It does have two LEDs of interest on it. It has that red, green, blue LED that gives you a bunch of status as to whether the board's plugged in correctly or not. There's another yellow LED on there that you can program through software. Also, that we haven't used yet. I'm not sure if we're going to use it. It's not that interesting. You have other LEDs to use, but basically through the addition of connecting feather wings to your board, you can add a whole bunch of other stuff in terms of input and output. So the feather wing the feather besides those two LEDs has no other outputs, and it has no inputs. Even the button that's on there is only a reset button, and that's not a very interesting button if all it does is restart your program again. You can't write a program that uses that button. So, and that's the reason why all the other stuff is in the kit. So the kit introduces other LEDs, buttons that you can actually read yourself from inside of a program. It's got sensors, temperature sensors, light sensors, got that rotary encoder on it. It's got a speaker on it, and it's got a number of other things that don't come to mind right now. But all those alternative input and output devices, one of which is done through a feather wing. For instance, the board that's got the rotary encoder on it sticking up, it's a feather format board in a feather wing compatibility format that it can basically be plugged directly next to the feather very easily. And there's a whole slew of boards that perform a whole bunch of other functions that you can make feather wings out of. There's little LED panels, there's little LCD panels, there are audio input and output devices, there are Wi-Fi and Bluetooth boards, there are plenty of things that you can put even on a small board like a feather. In some cases, there are some things that just physically can't be put on a feather, and those tend to get put on a board that I would say that you plug the feather into rather than the feather board is connected with. So actually I think I might have one here. There's like a 3-inch display. Not sure if I have a, okay, so here's an example. Here's a couple of examples of what you can put on a feather wing. So these are LED displays, so these are pretty crude. This is 40-year-old technology. But there's an electrical relay which you can use to turn off something that's AC powered. So whether it's a motor or a light switch or something, you can attach them to a relay. This is a GPS module, so you can carry it around, and it can follow you around and rat you out. So you could use to do so your parole officer puts one of these on your ankle, basically, along with a cellular modem to broadcast your location if you're ever cut loose from prison early. It's basically a feather board with a GPS module like this on it, and another feather wing, which is a cellular modem. So that's how you make an ankle bracelet. Here's a motor driver for connecting motors, for spinning things. These are boards that are very similar to the baseboard, to which I've modified and made I've added LEDs and buttons and servo headers and put some other things on that baseboard. There are another relay. There's a clock module. You can use it for keeping accurate external time. There's an LED matrix. And here's an example of a display. So you can actually use a real graphics display. This one's 3.5 inches. And so I typically say that you connect feather wings to feathers, but this is something that's so big that you actually connect the feather to it, just because it dwarfs. This is a picture of the bottom. So the feather is considerably smaller than the actual device you're connecting it to. So let's see how I'm doing for time here. Running long. Okay. So the feather format, like I said, it came out from Adafruit. format itself is 3 to 4 years old. It's very popular. Adafruit is cool. They're basically focused on folks like us. Their target market is basically STEM education. I might go so far as to say, I would say, go so far as to say STEAM education. So arts are actually a large part of it too. There's quite a lot of stuff that you can use in the arts field with microcontrollers. In fact, that was the original motivation for the Arduino platform that came out 10 or 15 years ago. Was that was designed basically by, I don't know if I would say artists with some technical ability, or at least the ability to work with people that are technical. But the Arduino came about because they wanted to have a way of being able to do interactive art demonstrations for installations. So you walk into a room and then this sculpture gets lit in a certain way. As you move around it, it interacts with you in certain ways. So those are the types of things that the Arduino was designed for. And clearly the range of possibilities for the things that Feather can do now that's 10 times as more powerful than that was are even greater. So the other thing is they tend to cater to makers and basically people doing custom engineering jobs. Um, so they are a medium-sized company, I guess I would say at this point. They're probably about 130 people. And they don't just solely focus on the electronics, although that is a big part of their business. They also have a bunch of people that are basically helping people go about learning how to design the packaging aspects. So they do a lot of 3D printing. They do a lot of cosplay stuff. So if you're into cosplay, I'm not. They do magic wands, and they do. They've actually one of the most recent projects I saw published was they did a pretty cool guitar. So I think the guitar was mostly done by buttons and stuff. I don't remember exactly, but it had a buttload of LEDs and stuff on it, and a lot of sensors for basically manipulating the guitar so that it makes noise. I don't remember exactly. I glanced over and it looked cool enough. But so they're tailored for people doing, one-off fun projects. They actually, a lot of Adafruit's projects get used by people in movie studios and stuff too. So a lot of special effects and things that characters in the production interact with are done sometimes with Adafruit products. So you typically don't see that they're Adafruit products when they're in the film or the TV show, but sometimes you'll see some behind the scenes, publications of these projects, and people do teardowns and stuff and show you exactly how they made them. So that's kind of nice. So the great thing about Adafruit is that they are very, very, very good about teaching you how to do the things with their products. So they are not like eBay or AliExpress, where they basically sell you something. They don't know what it is. They don't know how to use it. They can't answer questions from it. You give them money and they give you something. That is not what Adafruit is. Adafruit is teaching you how to get started with all this stuff. And some projects go to a fairly deep level. Some are dealt with a little more shallow level. So some people document projects, and these aren't necessarily people at Adafruit. These are people that made stuff with Adafruit, and they give all the documentation to Adafruit, and they publish it on their website. So there's an opportunity here for you to have a cool product or a cool project published on their website where tons of people see it. Certainly you can do that other places on the web, but since Adafruit is kind of ground zero for this kind of stuff, it's a great way to get publicity too. You can find yourself a job through an Adafruit project, Adafruit published project. So the Blackboard itself, so I do quickly mention there are some alternatives. We already talked about the Arduino. I don't know if I mentioned the Raspberry Pi or not, but did obviously mention the MicroPython board. But Feather boards and what Adafruit does, they aren't the only players in this space, but Featherboard, the Feather format's very popular, and Adafruit is very well positioned and very well, I would say, recognized and respected for the work that they do and the types of projects that you're going to be doing for senior project and for ME106, for example. So I always recommend when people start thinking about what they might want to do for an ME106 project is not only to look through the projects that have been published on the Adafruit website, but also just to look at the product catalog. And it's not until you know what sensors are out there and how much you can pay for them, how little you can pay for them, that you might think of a project is doable now that you never suspected that you could do for $100 or less. So, and $100 is even, I want to say it's kind of high. Some people have spent multiple hundreds of bucks on projects, but some people, $40, they can get by and they can do a reasonably decent, interesting project for ME106. So that being said, we're going to talk a little bit about the microcontroller board itself. It runs at a clock speed of 120 megahertz. This is much slower. Well, it's what, 2 orders of magnitude slower? Barely, well, megahertz, no. So it's 1 to 2 orders of magnitude slower than the processors within a PC. So from a computing standpoint, you can feel that difference. There's just a lot of things you can do on a PC you still can't quite do with a microcontroller yet, at least not 120 megahertz controller. It has a half a megabyte, 512 KB of flash. That is much less. That is probably 4 or 5 orders of magnitude less than the SSD or the spinning disk drive that's in your laptop or your desktop at home. Has 128 kilobits of RAM in it, which is, here we go. So this is 5 orders of magnitude less than the memory in a PC. This is also one of the reasons why I say that a lot of embedded systems are not meant for dealing with large amounts of data because they just can't store that much data. One picture, if you've ever taken a picture, transferred it to a PC from your cell phone and looked at see how big it is, those things can be tens of megabytes. Guess what? You cannot capture the image data from an image sensor and store it in RAM in memory inside of a microcontroller. The best you can do is kind of read it line by line and send it out to something else, like maybe onto a connected SD card or send it out over a network connection. But not only can you not read a high resolution picture, you just don't have the space to be able to even read it, not to mention process it. So if you connect a very low resolution camera, which you can get, to a Feather, you can actually do some useful things. I mean, I think for pixel from image sensor size of say like maybe 128 by 128 or 256 by 128, you can do some reasonably interesting things with an image sensor. You can detect when somebody moves into the room, into the field of view and out. So you can kind of follow what pixels have changed. But more than that, you're kind of pushing the limits. So for the most part, video is a stretch for a processor like this, but a lot of audio is doable. So Adafruit has demonstrated using a machine learning model that is compiled on a PC, the ability for a Feather with a connected microphone to be able to differentiate between a few different words. So the data machine learning model is smart enough that if you just put in all the sound data, it will pop out as to its best guess as to whether you're saying up, down, left, or right. So that's about the level of speech processing that the Feather can do. But similarly, so it can't process speech because that requires a lot of brain power. But the playing of audio, like the playing of music, for $15, you can buy a little board that you can plug in, 8-watt car stereo speakers into, and if you have an SD card that you can connect to the thing, you can put on MP3s on the. In fact, you don't even need an SD card. If you have an MP3 that's got a soundbite on it that's small enough to fit in the flash memory, you can play that audio back through the speakers, and it's got great fidelity. So it's not an iPod, but with some attachments, you can make it actually pretty close. So we can deal with the audio at a decent level. Speech, not so much. Video is a bit of a stretch. So the cool things that a microcontroller can do, and it's what microcontrollers were designed to do, is that they make themselves available very closely electrically to the environment through what are called GPIO, which are general purpose input-output. And basically all these pins that you see on a Feather board are the electrical connections. So once you solder the thing together, do I have a picture of a soldered together board? No, none of the pictures on the website. There we go. Well, it's plugged in. So basically all the pins that come out of the bottom of a feather board that I solder in for you guys are basically where the microcontroller does its electrical signal acquisition. So basically electrical inputs and electrical outputs are conducted through those pins. And the microcontroller that you have has 20 general purpose IO pins, 6 of which can be used for analog input. So, so for instance, things that are not digital, like light sensors, you can tell the difference between the different shades of light level, different gradations of temperature, etc. And I didn't mention it here, but there's also one analog output channel so that it can actually generate sound algorithmically. So you can generate your own sound waves actually through sine waves and stuff from the microcontroller. So basically, in a software fashion, you can generate waveforms through an audio amplifier chip, which is a couple of bucks, to actually play sound that is composed by the microcontroller, not just playing back of something that's been recorded and stored on an SD card. And as I've already alluded to, there are a bunch of feather wings that have a lot of these pre-canned functions on them, so of varying prices. So a lot of networking boards, display boards, sensor boards, all that. So I already mentioned where Adafruit publishes. I already mentioned that Adafruit publishes all their projects and their learning materials and stuff, and how to get started and how to basically execute some fairly sophisticated projects. That's all through the learn.adafruit.com website. So you can get there. It's one hop from the homepage. The homepage is here, and you just click on Learn, and you get to the learning system. In fact, I might be on it now. Yeah, this is the learning website. So a lot of projects, a lot of guides about how to do certain kind of things. So some are pieces of projects, and some are complete soup to nuts, right? So this little thing, obviously this, I don't know if this thing's actually moving arms or not. So this, theoretically, there could be 2 little motors in this. So I don't know if this is just a goofy animation, or if this could actually be an animated GIF of something that actually moves. But I can envision something like this actually being able to be done with a feather. If you had a motor, yeah, see, even these arms could be something just spinning around that's not symmetric and making it look like the arms move. So even something that moves like this could be done. You need 4 motors because it looks like the feet are moving too. But even something like this could be done with a feather board. So there's a lot of cute stuff you can do, especially if you're willing to go the extra route and do some nice 3D printing enclosures, or however you want to make an enclosure. So indirectly, I've already kind of talked about interfaces. An interface is basically just the border where 2 things meet, or it's in not a physical manner. It's also kind of a protocol, perhaps, between things that interact with each other. So you and I each have interfaces. So my interface on a good day, I have a happy interface, and I speak slowly and calmly. And if my mode, my state happens to be angry that day, my interface might change to be a little bit more of an angry, faster, more terse one. So it's not always the case that an interface is a physical one. So my interface also is primarily in English. So an example of a mechanical interface would be, when you put metal to metal, depending on kind of what precision you're doing that with, you can put metal to metal together. Sometimes you need a gasket. So the interface could be metal to metal, or it could be metal to cork and then cork to metal again. But it's basically that in-between area that 2 pieces like a valve head and engine block meet to cooperate with each other, because one side needs to do something to the other, or communicate some sort of state or information to to the other half. So electrically, this tends to be done through varying voltage levels or frequency in the case of things like Wi-Fi. And for us humans, our interface tends to be through language or gestures or even social norms. Like you might wave to somebody one way in some culture, and in another culture that basically means something that I probably shouldn't record here. So electrically, an interface, so IF is often used as an abbreviation for interface. If you started the lab, you already have gotten some sense for the difference between digital and analog. Here's some examples of some simple on-off digital sensors, buttons, anything that does threshold detection. So there can be temperature threshold sensors. So that would be different from a generic temperature sensor, which tells you the temperature along some sort of continuum. A threshold would be just tell me when it gets above 101 degree, because it's just basically a fever sensor. So that would be a digital type of sensor because it either is or it isn't in some condition. So light can also be the same way. It can be treated digitally as a too light or too dark kind of thing. Sound also, if there's sound or not, it doesn't have to be some sort of thing that listens and figures out what the sound is. It could just be, oh, there was a noise, right? The burglar knocked over my fancy statue off of that table where it's precariously balanced, and it sets off some sort of alarm. So proximity sensors are kind of the classic kind of occupancy sensor. And these simple interfaces are done through these GPIO, general purpose input output micro machines or nano machines that are inside the microcontroller. So to talk a little bit more about these little nano machines. So we think of a microcontroller itself as being a processor. Well, inside the processor, there are actually tiny little subprocessors. And these subprocessors do various things like they handle communications, they handle timers, they handle counting things, they handle electrical level protocols to talk to SD cards. They generate audios given just like a number, like the frequency. They would turn that frequency value, that integer, into a sine wave for you. So not all these things are done directly in software. There are sub electronics within a microcontroller that help manage all these other sub functions. So very similar to a car, right? The main purpose of a car is to drive. So its major input and output things are, the axle, the steering wheel, the gas pedal and the brake pedal and the ignition and all that. But there's a whole lot of other things inside, like the radio and maybe the car alarm and stuff that are their own subsystems that may or may not be integral to the primary purpose of the device, but may be there providing support functions. And that's what peripherals are, if you ever hear the term peripherals. So the key takeaway is that digital information are composed of a discrete set of values, similar to integers in Python. And digital in the purest binary sense means it's either on or it's off. So that's kind of the degenerate case of digital information, is one single bit of information, which is either true or false, on or off. And in contrast, there's analog. We've already talked a lot about analog. Analog is basically how much audio is done. If you are an audio buff, you may know that, at a physical level, audio is analog, but a lot of audio generation nowadays is actually digital. And the reason for that is some of it's for power reasons and some of it's for cost reasons. But even though it sounds like a sine wave, and if you look at it kind of at a high level view, it's a sine wave, but if you look down deep at it enough with like an oscilloscope, you'll actually see that it's actually digital. So how that magic happens is something you learn about in ME106. So other things that you use to that are analog are, capacitive touch sensing. that's a very physical, physics phenomenon, and that's all done at the physics level through analog functionality. So the key takeaway there is analog is basically when there's a continuous range of values. So it's the difference kind of between floats and integers in Python. Digital information is composed of discrete values, whereas analog or continuous floating point type values. So as far as interfaces are concerned, in the context of software, you've already seen interfaces. You've actually made some of your own already. Function calls are an example of interface. It's a way to get from one piece of code to another. And the interface is basically by being able to name the function and knowing the right number and the type and order of parameters. So you can get from one piece of code to another piece of code, passing data from one point to another through a function interface. And the return part of that interface is the return value. Most functions return values. So it's it's an interface through that is interesting. That data passes through in and out. It's like a pipe, right? So one term you may have heard of before is an API, which stands for Application Programming Interface. And it's basically just a collection of interfaces for a given set of functionality. So an API is in some respect, it's basically a library of functions that do a related set of things. So you can imagine in Python, you haven't done this yet, may or may not do it by the end of the semester, but you can draw stuff on the screen using primitives. You've done this, I guess, a little bit indirectly through Jupyter Lab. So using Python, you were able to plot. So all the plotting functions, and there's probably multiple plotting functions. I haven't used that myself very much. But there's a collection of functions that are used to render text in a graph, axes in a graph, and the actual plot data in a graph. So that's an application programming interface to plotting functions. So other types of functions or functionality that you might want to get access to are networks or more elaborate types of sensors. So you can imagine that an image sensor might have some fairly fancy functionality built into it. The ability to manipulate the sensitivity of the sensor and how to read the data out in one way or another at different resolutions. So the collection of functions that you use to get at a set of functionality, typically through an import statement in Python, is what's known as the API. So you've already used APIs. Lists have an API, right? All the functions that you can use on a list, that is the API for a list. Dictionary, same thing. Files, right? It's a limited set of things you can do with a file. You can open them, you can close them, you can read and write from them. You can get exceptions from those functions. So that is the application where you're the application. It's the programming interface to that set of functionality. I think later on you're actually going to be hacking Excel spreadsheets. I don't know if you're going to be authoring them through Python functions or if you're just going to be scraping data out of them. But there are APIs for being able to deal with data that's trapped in an Excel spreadsheet. So one thing you've seen already, and we've never talked about it explicitly, but a lot of these application interfaces are modeled as objects. So objects are basically data / variables that, sorry, I had to cut the chase, that have functions bundled in to the data, and they're treated as an abstract unit. So a list, not only does it contain the data, but as you've noticed already, it carries along functions with it. So the ability to be able to get the nth one, to be able to get the last one, to be able to append, right? So an object is, it's a type of data that has functions bundled with it. Now, up until you started using lists, if you remember, you were just using expressions and even just using functions before you even used your first abstract data type like a list. You were writing functions that took data and returned data. So in that sense, a function was just a filter. You could take any data and you could pass it to any function as long as it matched, the calling convention, the number of parameters and the type of parameters and the order of parameters correctly. But data were distinct from functions. In the general case, you could take any data and pass it to any function within reason. But the functions could be applied to different types of data. Now, this is in juxtaposition to an object, which the data knows what types of operations. It limits the operations on it. So it provides those functions to you with the goal of managing an abstract, higher level representation of data. So a list is different from a dictionary in different ways. They have different functions that go with them. You would never ask a list, what's a good example? You would never ask a list what its keys were like you would or could of a dictionary, right? So there's a limited set of functions and they're tailored just for the data that's manipulated by those functions. So we may or may not have you learn how to create your own objects in this course. In the first semester we did, the previous semester we didn't. So it's not clear how this is going to shake out. But it's kind of nice to see how objects are created, and they're not that complicated at all. In fact, if you want to see how all the objects are created, we're going to get to this next, but you can look at the source code for the API for all the components that are on your board, and you can see that it's just regular old Python like anything else. It's just that it's organized a little bit differently. You can see where the data and the functions get bound together into one module. So here we are, we're going to talk about that now. So I have created for this course an API specifically for ME30 so that using abstractions, data abstractions, object abstractions, you can get at all the components that are on all the boards of your kit. So rather than having to understand at the electrical or the electronic level, or even having to use the lowest level functions in CircuitPython that check the electrical values of pins, I've created abstract objects that you can just create that perfectly model the components that they pair with. So the simplest example is a button. You've already seen, if you started the lab, that you create a button object and you can interact with it. Now, if you think about what a button does, so this is kind of like the list example that I gave before, there's some things that it makes sense to ask a button of, just like a list, right? What does it make sense to ask of a button? Well, there's really only one thing, is whether it's pressed or not. So whether it's up or down. You don't care about the color. From a software standpoint, you don't care about the color. You don't care about its size. You don't care about what it's made of, right? The only thing that you care about as far as having a button, access to a button is concerned, is to whether it's pressed or not. So I created a data type, right? Like a list, like a dictionary, like Python has done for you. I created a button for you that you have one question that you can ask from it, whether it's pressed or not. And similarly, from every other component on the board, the LEDs and PWMable LED, which I think you might be doing in the first lab, and the encoder that's on the board, and the potentiometer, and the ambient light sensor, and all these have devices, all these have objects that you can create by these names that you can ask very specific questions of or command very specifically. So let's just march down through the list. What does it make sense for a generic binary LED to be able to do? Well, you need to be able to turn it off, and you need to be able to turn it on. If you want to get fancy, you can tell it to toggle itself. So if the LED knows that it's on and you tell it to toggle, it turns itself off. You don't necessarily need toggle, right, yourself. You could have done this yourself. You could have remembered that the LED was off, and that if you want to toggle it, if you want to change it to its opposite state, you would have to remember that it was off, so that you would have to have an if statement that says, if I'm currently off, then I want to turn the LED on. But I just added a function because it's something that you may want to do. And it's easy for me to provide to you, just this toggle function. So LED PWM, I don't know if I want to go too much into this, but it's basically a way of being able to take the LED and to turn it on at a certain level of on or offness, right? So it's a dimmable LED. And you give it a fraction from 0 to 1, if I remember correctly, as to how bright you want it on. The encoder, I think, I'm not sure if you've dealt with this in the lab or not. It basically returns you the current count as to how far you've turned it clockwise versus counterclockwise, and it returns you an integer. So if at the beginning of the program the count was 0 and you turned it clockwise 3 clicks, then if you call the count function, it returns 3. And subsequently, if you turn it to the left 6 times, it would return you -3 if you asked for the new count. Potentiometer, you have seen this, I believe. It returns a floating point value from 0 to 1, depending on how far around its mechanical rotation it is. Ambient light sensor, from its minimum to its maximum level of brightness that it can differentiate, is also from 0 to 1. The servo, you give it an angle from 0 to 180, I believe, that you ask it to point to, and it does it. So it doesn't make sense to ask anything else of a servo. So electrically, a servo can't tell you what angle it's at. So that would be nice, but electrically, it can't do that. So the only thing that makes sense to be able to do with the servo is to be able to ask it to go to a certain angle. A speaker, you give it a frequency to play, and it plays it until you either turn it off and tell it to stop. So I believe there's also a missing method here, missing function called off or stop that you call to get it to stop making whatever frequency that it's playing. And temperature sensor, of course, there's only one thing you can ask it for, and that happens to be the current degrees in Celsius. And all this stuff is in the API_EduShields module that you import. And you are more than welcome to take a look inside of that to see how it does its magic. And hopefully by the end of the semester, you'll understand enough about not only how the components work from a high level, but your knowledge of Python will also hopefully provide you enough expertise to be able to go in and figure out at a fairly detailed level how these objects are modeled and actually work when you call them. So right now you just have to treat them as software objects, but in fact these software objects have an interface to electronics inside the microcontroller that do electrical things and go out and make noise, make light, move a motor, etc. And the demo program that does all that is also out on your board. I believe when I put it out on the board, I called it code.py because it has to be code.py for it to run. Internally, myself, I call it full demo. And I think I encourage you in the lab when you are starting to write your own code for your microcontroller board in one of the exercises or in multiple exercises that you rename that code.py back to full demo, because that's what I call it. So if we all call it the same thing, then we can just refer to it by the same name and everybody knows what we're talking about. So that program, I think it even says in the comment header that it's full demo.py. So in summary, the programming hardware uses the ME30 API just like you do any other type of programming to manipulate something that doesn't have a physical presence. So a file kind of doesn't have a physical presence. It's modeled as a file object that you can do read and write and open and close and stuff on. All the components on your kit's boards are modeled as software objects that you just call their methods on, their functions on, and you get them to do things. Or you ask questions of them as to what their current state is, like the light sensor or the buttons. And you'll learn a lot more about the lower levels, both electrically and at the software level, how to talk to different types of sensors and stuff. So this lecture went on a lot longer than I hoped it would, but you do have the option of going back and listening to it as many times as you want, and or speeding it up or slowing it down. So I hope this provides you enough kind of background information as to why we do this, how it's done, how the kit is used in future courses and why you would use it in future courses. And basically, it's a preview of things to come in ME106, and if you continue on in through the mechatronics track, through the capstone course. So I hope this was informative, and I apologize for it being so long, but it is what it is. I could talk about this stuff all day, but for 2 units, there's a limited amount of time where I can do this. But if you have any questions, feel free to contact me directly. Some students want to know more than I actually want to tell them sometimes, and I typically just say, you're going to learn about that in ME106. I will not tell you everything. Maybe you want me to tell you, because ME30 students also can be sidetracked very easily. And I actually want you to focus on being successful at the level of the material that ME30 teaches you and that you need to be responsible for. So last semester we had projects where you could kind of design your own project and present it to the course, present it to the class at the end of the course. And I got a lot of questions from students that had really high expectations or aspirations as to what they wanted to do for their project. And part of what I had to tell them when they asked me questions was, you don't want to do that now because it's too much. And some students would also ask me kind of the opposite. They would ask me about things that were really simple and whether that was enough for a project. And I would go, no, you need to be a little more aggressive than that. You need to come up with some more elaborate ideas. So some of the answers you get from me might be directly answering your question, but they might also indirectly just forward you to stuff that you're going to learn later on in ME106. And I'll ask you to be patient and wait until then. So that's it. Good luck.